Now I'm going to present my research on optimizing the performance of parallel discrete event simulations, or you can call it a PDES, through a method called Profile Guided Partitioning. And this work was driven by a key challenge in larger scale simulation and how to scale efficiently across distributed computing environments while managing communication overhead. And PD is widely used in areas like circuit simulation, network modeling, and storage systems. However, as simulations grows in complexity, and parallelizing them is not always straightforward. One of the biggest roadblocks we encountered in the overhead caused by frequent communication between distributed components. And our approach attempts to solve this by analyzing communication behavior in a sequential run and using that data to guide how the simulation is partitioned across nodes. And in the next 30 minutes, I'll walk you through the background of this problem and explain you the method that I developed and show you the results from several benchmark models. And I will also share some broader implications and ideas of future work. Yeah. And we'll begin by introducing discrete event simulation and what is it and why it's important. Then I will discuss parallelizing the discrete event simulation and also the communication challenges that we encountered, which is bottleneck for this problem. And from there, we'll go into the proposed solution like profile guided partitioning. And I'll explain you how it works in detail, and we'll look at how we collect profiling data and how we use graph partitioning tools to organize the simulation model and why this strategy significantly improves the performance. And then I will present our experimentation setup and walk you through the results we observed on number of benchmarks, including some of the key data sets which we simulated. And finally, we'll wrap some key takeaways and broader implications of our approach, just beyond just simulation, and we'll look further directions for this thing. Yeah. And comes to the basics, and discrete event simulation is just a modeling technique used for systems where the state changes at specific points in time, these points being events, and in construct to continuous simulations where the model evolves in fixed time steps. And this is particularly effective for systems like digital logic circuits, telecommunication networks, and manufacturing workflows, where actions are triggered by discrete events like message arriving or job completing or signal flipping. And in DES system, like you have objects representing components in the system and events that move between them. And the simulator maintains a event queue and process events in timestamp order. And because it only simulates what's necessary, the state changes. And D is often more significant than continuous model. And however, when the system becomes very large with thousands of interaction objects and millions of events, even DES becomes computationally expensive. And that's where the parallel DES comes into the picture. And as simulation grow, we know the more the complexity also grow. Like for example, when modeling a multi-core processor or national-wide logistics network, the number of simulation objects and events can scale into the millions or sometimes even billions. A single core or sequential DES engine can't handle the load efficiently. So to scale up, we turn to parallel discrete event simulation, or you can call it as PDES. The basic idea is to divide the simulation model across multi-processors or nodes, and each processor simulates a subset of the objects and processes the events related to these objects. That means like they need to exchange messages across nodes, and the communication introduces latency. The cost of communication in a distributed system is orders of magnitude higher than the local memory access. Like when thousands of messages are exchanged per second, this overhead becomes significant. Like even worse, when processors often need to synchronize to previously casualty or adding further delays. So while PDES promises scalability, it only works well if we minimize communication between nodes and balancing the computational load and that's where the contribution comes in. As we know, like one of the most fundamental challenges in PDEs is like cost of inter-process communication. Like suppose like imagine two simulation objects, says gates in a digital circuit that frequently exchange events. If these two objects are assigned to different processor, like every message they exchange must go through the network stack. Even on a high performance interconnect like infinity band, this adds delay and also reduce simulation throughput. Like now imagine this happening millions of times during the simulation. The communication overhead can quickly overwhelm any gains from the parallelism. And also it leads to idle processes and synchronization delays and degrade performances. These problems became like lightweighted events, more severe with the lightweighted events and small messages that are cheap to compute but expensive to send over the network. In those cases, the communication cost dominates the entire simulation time. So we arrive at a bottleneck, like how do we partition simulation objects across processors in a way that minimizes the intercommunication messaging? And that is the central problem we address. And if we can solve that, we can unlock the performance potentials of PDES. And also like we have two computing goals like when partitioning the simulation model. First is to minimize communication between processors, so we don't spend most of our time just passing the messages. And also the balancing the computational load across processors, so that no processor is overloaded while others are idle. These goals are often in conflict, but if we just group all highly interactive objects like together to reduce communication, we might create an imbalance where one processor does most of the work. On the other hand, if balanced load blindly without considering communication, we could end up with ton of inter-process messaging. The key is to find like smart partitioning strategy, one that understands how the simulation behave and uses that how to guide the layout of objects across processors. And this is where our approach comes in, like a method that builds a communication profile of the simulation before parallelizing them, and also use that profile to drive like partition processing. And several researchers like have explored this profiling like to guide simulation optimization. Researchers like Buhalkar introduced like a dynamic profiling for partition adaptation during simulation, and Goham who used like 5 spread models to create profile-based spatial partitioning, but their approach was tailored to a single application domain. And Pishola proposed like entire dynamic partitioning, but required runtime system integration and feedback loops. Like, and how our works different from there, like in a key ways. Like we use like offline profiling, like one sequential run is enough. This avoids runtime overhead and complexity. And also we focus on general models, not application specific systems. And our profiling results feed into a well-established like fast partitioner algorithm, like no custom tools needed or nothing. And this makes our approach scalable and easy to adopt and portable, and it can be plugged into existing simulation pipelines with minimal changes. In short, we build on early work, but with strong emphasis on practicality and broader complexity. And there goes our solution, like profile guided partitioning. The idea is simple. Instead of jumping straight into the parallel execution, we first run the simulation in sequential mode, like where everything is processed by a single core. And during this run, we record all the messages that are exchanged between simulation objects, like whom talks to whom and how often. With this data, we build a communication graph where each object becomes a node in the graph, and each edge represents communication between a pair of objects, and also the edge reflects like the frequency of messages between them. And once we have this graph, we apply a graph partitioning algorithm like that splits the graph into chunks, and each chunk responds to the corresponding to the processor. And the partitioner tries to balance the number of nodes while cutting as high weight edge as possible. And this means that like frequently communicating objects are placed together and minimizing the number of cross processors messages during the actual parallel run. It's a simple idea like profile first, then partition, but it has huge impact on performance. And yeah, let's walk you through like what it looks like conceptually. And like after the profiling phase, like we constructed a weighted undirected graph, like where each node represents a simulation object and the edge represents number of messages number of messages sent between the objects during the sequential run. Like I can give you another example. Like if an object A sends 500 messages to object B and B sends back to A 300, then the total weight of the edge between A and B would be 800. Like now the task is to like partition this graph into like n parts, where like the n is the number of processors or nodes in the parallel system. And next one is like profiling phase. Like in this phase, like we focus on collecting the data that will guide our partitioning, and we instrument the simulation to track every message that gets sent during a sequential run. So for each pair of communicating objects, we log who the sender and the receiver was and the number of times they communicated. And optionally, we can track the message sizes and the timestamps. So at the end of this run, we aggregate this data into a message frequency matrix, and from these we build the weighted communication graph we described earlier. And this profiling step is relatively cheap. It's just a single thread run without logging, but it gives us valuable information like about the model's communication structure. What's more powerful about this method is like that it is at a domain independent. We don't need to understand the application internals or make any assumptions about its structure, whether it's a storage model, a network simulation, or like a logic circuit. This profiling approach works the same way. And this is the heat map that shows the actual communication profile of one of our benchmark circuits, ISCAS 89S9234, where like the each cell in the matrix represents the volume of messages exchanged between two simulation objects. And the color indicates the intensity, like red for high communication and frequency and blue for low. As you see, like there are few dense clusters where certain group of objects communicate heavily with each other, and these clusters are like ideal candidates for co-location, and meaning like they should assign to the same processor to avoid expensive internode messaging. And this heat map is like visual confirmation of the power law behavior like that often emerges in simulation. A small set of objects account for a large percentage of total communication. Like this visualization helps us like identifying natural partitions in the model and validates that profiling data is rich enough to inform effective partitioning. In the next slides, like we'll go through the partitioning algorithm and how to create low communication partitions and compare the results with the tradition. Yeah. We are using like Yummy TIS, like a highly effective used like graph partitioning library, and it is particularly well suited for these kind of work because like it supports weighted graphs, and so we can account for message frequency, and we can also provide balanced partitioning, ensuring a even distribution of computational work. And we uses advanced techniques like multi-level recursive bisection to quickly find near optimal partition even in large graphs. So we configure METS to treat all simulation objects as having the equal weight, like which means like we primarily focus on balancing the number of objects per partition, and the edge weights which we reflect communication frequency like guide METIS to minimize the cross partitioning connections. So the key insight here is like we are turning a performance bottleneck into a graph optimization problem, and METIS helps us to solve this problem efficiently. And the output of this process is like a partitioning map tells us how simulating objects should go which processor with minimal expected communication during the parallel execution. And here, like in the random strategy, we are constraining between two different partition strategies, like random assignment or profile guided approach. And in random strategy, simulation objects are distributed to processors without considering how often they communicate. It's just blindly, we are just assigning, it's just assigning to the processors. And this method is like easy to implement, but leads to a large number of messaging crossing processors boundaries. And because frequently interacting objects are often placed far apart. On the other hand, profile guided method uses actually messaging frequency data to drive the partitioning process, and objects that communicates a lot are grouped into the same partition, and this reduces the cross node messaging drastically. And we'll see the difference clearly in the next slide. So we visualize the communication heat maps under both strategies. But even at this conceptual level, the idea is clear. Like by clustering high traffic uh, object pairs, we keep the communication local and make the overall simulation run much faster. So it's important to note both the methods preserve functions correctly. But the extended performance between them is also often massive, and we'll correct that. We'll show that concentratedly with benchmarks and runtime comparisons shortly. Here we see the communication pattern for S9234 circuit when using random partitioning. This heat map visualizes how much communication is happening across partitioning boundaries. In this case, the model was split into 4 partitions, and you can clearly see that communication is scattered and across the board, and high traffic edges are spread across partitions, meaning that most messages now have that cross node boundaries, and this results like 76% closely. Like the actually is like 75.83, but I mentioned it like 76% of messages in the simulation like end up with interpartition, that is like they must travel over the network. The significant increases the communication overhead. Like this reduces synchronization's efficiency and ultimately slow down the entire process, entire simulation. And this isn't just a worst case example, it's representative of what happens in many practical simulations when no attention is paid to communication patterns like during partitions. Also, the next is like now let's look at the circuit uh, S9234, like, but this time partition using our profile guided strategy, and you'll immediately notice how much concreted and localized the communication is. Like the majority of high traffic communication now lies in the same partition. As a result, like only 1.4% of messages cross partition boundaries compared to the 78% on random partitioning. This is like massive improvement in communication efficiency by simply exchanging the way we assign simulation objects to processors. And using profile guided data, we have eliminated most of the costly network communication that offers in a parallel simulation. The difference here isn't subtle, but it's difference between an optimized scalable simulation and one that suffers from network bottlenecks. And also, this is where the power of data driven simulation engineering becomes like clear. Like we are also using like actual communication behavior to make intelligent layout decisions, and the result is faster and more scalable simulation. Let's talk briefly about the experimentation environment we used to evaluate our partitioning method. We run our simulation on Beowulf style computing cluster, where like each node is equipped with quad core Intel Xeon processors running at 2.33 gigahertz. Each processor is like hyper threaded and runs on standard Linux environment. For intercommunication, we use like OpenMPI library. We tested our approach on like 2, 4, and 8 node configurations, like which directly corresponds to the number of partitions in the simulation. So, and our goals was to evaluate two things, like how does our profile guided method compare to random partitioning in terms of runtime performance, and does the scalability trend holds as we increase the number of partitions. We applied both strategies like random and profile guided to the same set of benchmark models using identical system settings and simulation code and workloads. The only difference was the partitioning. This setup gave us a fair and robust basis on comparison and allows us to isolate the impact of partitioning on performance. And benchmarks we used are ICAS 89 digital circuits and RAID storage control simulation and mix of structured and irregular models. And we use like medium circuit, S5983, S5378 is like medium sized circuit. And we tested this circuit on 2, 4, and 8 node configurations. Like in each case, we compared the total runtime. Here on 2 node, we can see there is like 2.5x speed up of executing for the partition profile guided. And on 4 nodes, we can see like 2.15x speed for the profile guided. And then for on 8 nodes, we can see like 2.1x profile speed for the profile guided over the random algorithm. And this tells us like even for moderate complex models, like communication aware partitioning provides significant benefits. And as we increase the number of partitions, the challenge of preserving communication locality grows, but our method continues to deliver strong results. The same thing for like S9234 dataset, like the difference is dense and high communication circuit. And on 2 nodes, we can see like 6.04 speed up with profile guided partitioning, and then the same for the like this. There is a huge difference for the node 8 and node 4, and but we can note that the decline in speed up as we add more nodes. So this reflects like increasing difficulty of keeping all high traffic objects together in small partitions. And also we took one of the large data set, large benchmark in our test suite. So here also we can see there is a huge difference between the runtime execution for profile guided. And the same like in RAID model also, where the data is of similar type, we can see like 5x speed for the profile guided thing. And then here is the summary of the results. Here is the speed ups, like the comparisons, like how many nodes we used and what are the algorithm we used, like, and this is the speed comparisons. And we have observed like few trends, like first for models like RIDE, where communication is structured and relatively predictable, and profile guided partitioning performs consistently well. Models with like regular structure and RAID, like example RAID, will benefit more. So the key takeaway is like partitioning effectiveness depends not on size but also on structure. So profile guided partitioning is particularly powerful for models with skewed or localized communication, and it also continues to deliver value even for structured models like RAID storage. And why it works, like by using profile based partitioning, we achieve 3 key benefits. And communication locality, that's the one of like most messages stays in single partitioning, like avoiding like slow network transforming. And this also improves like synchronization, like with fewer cross node events. The simulation requires few synchronization points, especially in conservative or like optimized models like time wrap. And also this maintains the load balance. Like METIS helps ensure like each processor receives roughly equal work, like avoiding idle time of hotspots. And for regarding the future work, like first we plan to explore like dynamic partitioning, like where the simulation can adopt its own layout at runtime as communication patterns evolves. And this is especially useful for time varying models like mobile networks or adaptive systems where the workload shifts during the execution. And second, based on like hybrid approaches that combine profile guided partitioning with like specific domain. So, and like for example, like in circuit simulation, we could leverage gate level topology to augment the profile data. And third, like we are looking at using machine learning like to predict partitioning layouts instead of profiling every time. So there also like the question of like energy efficiency, like the by minimizing the communication, we are not just improving the runtime, we are potentially reducing the power usage as well. That's an area we hope to explore in future. And regarding the broader implications, like this partitioning approach has like different uh, applications like this can benefit from distributed database or like real-time analytics engine or agent-based modeling or federated simulations in digital twins, something like that. And yeah, let to summarize the whole presentation, like parallel discrete event simulations are often bottlenecked by uh, communication, like not computation. And this means that even highly parallel systems can underperform if simulation objects are assigned inefficiently. So our solution like profile guided methods shows like real world impact and uses a significant profiling. Yeah. And these are the like system level details of the environment we used for testing. And yeah, that's it. Any questions?
Let's see. There are a couple of questions that in the Q&A system here. So the first, do you know which HPC databases have support for PDEs? Oracle Exchange or SQL Server or something else? This looks useful for digital twins.
Oh, regarding the databases, regarding the HPSC, I'm not aware of anything like maybe like for event queues, like object graphs, those kind of databases would be useful for this, I guess. Like or no
Okay.
SQL databases, like if we are storing large volumes of structured event data.
Yeah, and the
Yeah.
yeah, George Carlisle said Oracle has graph and vector databases now. So I think that
No, the vector database like nowadays it started evolving, right?
yeah.
For machine learning all these tasks.
Great. And the other question is Metis. Is this the NIST Metis or something else?
Sorry?
You mentioned METIS.
METIS. Yeah.
Medius. Okay. Is that the NIST?
METIS. No.
Okay, this is a different. Okay.